Okay, so now that we saw how to use the Pandas library to load data and to do some basic operations with data, we're going to look at how to use Pandas to help us visualize our data. So we're going to look both at plotting data from data frames using the data and then doing the plot outside. I'm going to show an example of that. But this is just to illustrate that you don't have to use the Pandas interface for plotting whenever it's not convenient. But most of the time it will be convenient, especially if you're doing just a basic data understanding step, analyzing your data before starting your actual work or something like that. And so it's very convenient to plot directly from a series or data frames object. And we're also going to see how we can group rows by some value and then plot the result. So let's go again to our star catalog data. We have this CSV file we saw previously with the distances, magnitudes, spectral types, and so on. And we saw how we could read from the file, the CSV file. Here I'm going to also import Pieplot, so we're going to do some additional plots without using Pandas. But I also import Pieplot because I set the style to Seaborn. So this is not mandatory. I just like this better than the default one. But also, if you want to use your own style, you can just start your scripts with these lines. You import matplotlib, and then you set the style to whichever you want. Note that you can also write your own styles if you have some very detailed specifications, for example, for some document or something like that. You can use that. And so this is a practical way of setting the style. And then even if you plot via the Pandas library, since Pandas is also using Pieplot behind the scenes, so to speak, you can also set the style for all those plots that you're going to do. So this is just to read the data. We saw that we could use value count to get the most common spectral types, and now we can we can do a histogram, for example, for the magnitude of the most common type. We take K0. So here we are counting the unique values of the spectral type. We get the one with the highest count, so the one that is in first place in the count series. And now we get from our table, from the column with the magnitudes, those entries corresponding to the indexes where the spectral data column is equal to this K0. So this type, the most common type that we have here. So this is one example of how we can extract the data that we want. So from the table, we want the column with the magnitude, but from this column, we only want those values that correspond to a true value in this comparison. So taking the spectral type data, we compare with the most common type, and if this is true, then this is one of the values that we want from the magnitude. So this is an example of how you can get data from one column in your table according to some condition on some other column of your table. And now we create a histogram, and this you can do it simply by calling the hist method on the series. So this series, mcabsmag, is the absolute magnitude of all stars of type K0. And now we plot the histogram using 50 beans by just calling the hist method on the series. So this is the histogram for our data. So this is a very easy way of visualizing the data or some part of your data. You just extract the data you want and you use these plotting methods in the data series or also in the data table, depending on what you want to use. But one thing I don't like with histograms is this binning effect, because depending even of some very small variations in the values, they can fall into different bins, and you can get a very different histogram. So it's discontinuous in that way, and that is not very good. So we are going to use kernel density estimation. This is a method that uses a kernel function, and a kernel function in this sense is a function that is symmetrical and has a total area of 1, and it's always positive. So symmetrical means that it's the same value for minus x as it is for x, and it's always positive and with an area of 1. This can be something like a triangle, a Gaussian curve, quadratic curve, things like that. So you have lots of different functions that meet these criteria. We're going to use the Gaussian function for this. And the way you compute a kernel density estimation is by adding for each point, instead of what we do with an histogram, which is summing all the points or counting all the points in each bin, we add for each point a continuous kernel function centered on that point. So let's say we are using these Gaussian functions. This point here at -4 contributes with this part here, this Gaussian function. This point here at -1 contributes with this part, and these 3 points with this here. When we add all these red Gaussians, we get this curve like this. So this curve gives us the distribution, or the density of the distribution of these points, but using this kernel function to smooth the curve and not have those jagged edges that we get with the histogram. So let's use the same thing. Let's represent this histogram with a kernel density estimation, so we get a smoother representation of the distribution of values of the magnitude for this type of stars. Instead of having this representation here, we'll have something like this. Okay, so one thing you can do is, instead of using the hist method here, you also have a kernel density estimation in the series. So you could just use that method and get this result. But there is one thing that I didn't show you so far, which is how we can draw these kinds of curves with plotting. So far we saw how to plot some specific values where we have x and y, and we draw the lines or the plots. We saw that last week. But for drawing these functions, we need to take some extra steps. And also I'm going to show you that if you don't have a specific graph that you want in Pandas, you can just get the data and plot it yourself outside. So this is what we're going to do for this particular example. We're going to use the SciPy library. I'm going to talk more about the SciPy library next week, but today we're going to use from this library, the stats module, we're going to use this Gaussian kernel density estimator. So this is basically the function that computes this thing. We have a set of points and a Gaussian curve, and it adds up the values for all the points that we give it. So we're going to use that to compute the kernel density estimation, and we're going to create here a plot function that receives as input the values for which we want to estimate the density. So this is a set of values that is something like this here. So for example, -4, -1, 1, 2, so on. And we are going to represent how densely packed they are in different places. So in our case, what we're going to do is do that with the absolute magnitude of the K0 stars. So here there are a bunch of values of magnitude. Then here there are very few, and there are a lot more densely packed in this range. To do that, we're going to get the extreme values, the minimum and the maximum of our data values. This tells us the interval in which we're going to plot our kernel density estimation. And now we need to create a set of points along the x value in order to draw this line. So remember that plotting takes x and y values and then joins them together with straight lines. If you want to draw something that looks like a curve, you need to have lots of values here and lots of values on the y-axis corresponding, so that this will be done in very small steps and it looks to be smooth. So to do that, we will use from NumPy the linspace function that receives as arguments the smallest value, the largest value, and the number of steps that you want to take, the number of points that you want to create. And this gives you uniformly distributed points between the minimum and the maximum, and as many as you specify here. So if we specify, for example, 200, we will have 200 values uniformly distributed along this axis, and this is enough to create a smooth plot here. Okay, so now we're going to use the Gaussian kernel density estimator. We're going to create this kernel density estimator function or object with the data. This is how it works. When you call this function with some data, it creates an object that stores the data and is ready to compute these kernel density estimations for any value that you want. For example, if you had this data, if you gave it value 2, it will give you this point, which is the sum of these Gaussians at x equals 2. If you give it value 0, it will give you this point, and so on. So this is what we create here with Gaussian KDE. We give it the data, and we have this callable object that works like a function that will give us the values that we want. So now to plot our graph, we give this object these x values that we created. So from the minimum to the maximum, all the little steps. And so it computes the y values for this and returns a tuple with the x and y. I just put the parentheses here to remind you that this returns a tuple, but in reality you can just write like this. So this is correct also in Python. But this is just to let you know that when you return more than one value, the function returns a tuple with all the different values. So we can use this in this way. We're going to get the first 5 elements here. So this is basically, we use the value counts to get the how many of each spectral type we have in our database. And so we can get the first 5, which are the most common, the 5 most common spectral types. And now for each spectral type here, we're going to get the absolute magnitude. Okay, I have a typo here. We don't need this row. We're going to get the absolute magnitude of the stars of this spectral type. So from our table, the column with the absolute magnitude, we want those values for which the spectral type is whatever we are measuring here. Now we send these values to our function that will compute the kernel density estimation. Now here is the important trick that sometimes will, if you miss this, sometimes you get some problems, which is this absolute magnitude variable here is pointing to a data series. So these have indexes and values. What we want here in our function is just the values, just the data. So a NumPy array with all the values, and we don't care about the indexes. So if you want to do this, if you want to get only the values from the data series as a NumPy array, you can use the values attribute here. So absmag.values will give me just the absolute magnitudes as a NumPy array without the indexes. So this is no longer a series, and I can use it wherever I can use a NumPy array. So in this case, I can do the plot with 100 points or 200 points or whatever I want. This is just the number of steps that I'm going to use for the line. The more points you use, the smoother the line will be, but the result will be mostly the same. And now I have the x and y values. So these two values that come as a tuple, I will unpack here into these two variables. And now I do the plot using the x-axis, that series of numbers created here with linspace, and as the y values, the kernel density estimation for all for my data on those particular x values. Okay, so I can do this 5 times for the 5 spectral types, and then I can create a legend using the names of the spectral types. So this is basically, there are two ways of doing this. One way would be during plot, I would say that the label is the spectral type, and then I would not need to have this in the legend, because each series would have its name defined. Or if I don't add labels during the plot, I can then later, when I create the legend, give a series of strings, or for example a series, a list with strings, as long as it's an ordered array, which has the same number as the series I want to represent on the legend. So plot will associate them in order with the data series. Okay, so this is the result. We have here the 5 most common spectral types in order, K0, G5, and so on. And we have the kernel density estimation curve for all of them. Note that these distributions work similarly to an histogram, but they smooth the curve, smoothen the curve a bit, because they use this Gaussian kernel to add up the contributions of the different points. So this is an example of how we can do this kind of representation, taking the data from the Pandas data series. So in this case, we actually take it as NumPy arrays. We take the values and then we do the plotting. But in many cases, we're going to use Pandas for doing the plotting. So in case you need to do some specific plot that it's not easy to do with Pandas, you can do it outside. But in many cases, it's easier just to use the functions in Pandas. For example, let's go back to the public spending table, which we have this column with the price of each contract. And let's say we want to plot the cumulative costs, the total costs so far along the days of all these expenses. We have this cumulative sum methods in the data series. So if you ask for the cum-sum result, you get a new series which has the cumulative sum over all the elements of the series that you had originally. So this total cost is a series that for each entry has this cumulative sum. And now we can do the plot of this series. So I'm saving the file here. You don't need to save if you just want to see it. But this would be the index. So the index is just the position along the row. And this is, as we go along the table, how the total cost is rising with time. We can also do the histograms. We saw previously, we did the histograms for that K0 spectral type. This is a bit different. We want to do 2 histograms for the expensive contracts and for the cheaper contracts. So expensive is more than 50,000 euros, and we can select from our table those contracts that have that cost more than 50,000 euros. So I do this in 2 steps. I create a mask which has the Boolean values with the true value for all the contracts that are more expensive than 50,000, and then I select from the table these rows, and I do the histogram here. So this usually works. You can use the table and add just index it with a series that will follow along the rows, because Pandas can notice that the series you provided has the same index as the table. But often, if you want to be explicit, or I think you get some warning messages in the more recent versions, you should use the lock here. This would be probably safer, because here you are actually saying explicitly that you are looking at the rows and not the columns. But Pandas is quite flexible in this way. Sometimes you can get away with these kind of things because it can understand, so to speak, what you're trying to do. But it's often safer to be explicit. So this would be the recommended way of doing this, getting from the table the rows that correspond to the true values in that mask. And now we get this in the series, so or in the data frame, sorry, because this has the complete rows. And now we can plot just the price from this data frame here and do the histogram. So this would be the expensive ones and the less expensive ones. These ones are capped at 50,000 and these ones go all the way to several million. So now let's do something a bit different, which is looking at the different types of contracts. We're going to compute the mean cost of each different type of contract and then create a bar plot with all these values. So the first thing we need to do is to group all the rows in our table according to the different types of contract and then get the mean value for each group of the price. This is easy to do with Pandas because you have this group by method on the table where you can specify which column or columns you're going to group by. So all the rows that have equal combinations of values in those columns will be placed in the same group. In this case, all rows that have the same type of contract, we will place them in the same group. And then you can select from these groups something to extract. So we're going to compute the mean value of the price for each of these groups. And what you get with this operation, with the group by operation, is a group data frame, which is slightly different from the regular data frames, where you have the different groups. So according to the type of contract, you have different groups here, and each one has the mean value of the contracts or the price for each group. This is just one step. We can now go one step further and convert this group data frame into a real data frame, so a normal data frame, and we can do that with this two-frame method. So now we have a data frame that has these the types of contracts as an index, and the contractual price is the column of the data frame. And if we want this in a data frame that has two columns, one with the type of contract and one with the price, we can just reset the index. And remember that when we reset the index, Pandas will create a new index and copy the old index into a new column in our database. So in our table. So this is the kind of steps that you can take. This may seem a bit confusing at first, but when you get used to this, basically what we did here is we grouped everything by the type of contract, and to each group we associate the mean of the price. And this creates a group data frame. It's a special kind of object that stores this group information. And then we converted it into a regular data frame and we reset the index. So now we have two columns, one with the column we use to group the rows by, and the other with the column we use to compute the mean. So now it's easy to do the bar plot because we can just say that from this average price, so this data frame here, we want to do a bar graph. We can use plot.bar, and we use these two columns. This column, tipos de contrato for the X labels, and the price for the Y values. And we get a bar plot like this. So this worked. We have the different contract types here and the mean values here, but this is not very good because with this shape it's hard to read and it gets very small and so on. But fortunately you have different options. If you use bar, the bar plot, you get these vertical bars, but you can use the bar age plot, which is the horizontal version. So for this case, horizontal works better, and we can, well, with this graph it's very small, but if you use a larger plot, you could read the actual categories there, and it looks better this way. So to sum up, we did in this example, first grouping everything according to the type of contract. We computed the mean for each group. Then we converted this into a data frame, resetting the index, so we have the two columns. And now we do the plot with the two columns. So the types of contract for the X values or the X labels, and the price for the size of the bars. Okay, so now let's look at the diabetes example and see a few other visualization techniques that we can use with Pandas. One very useful way of visualizing distributions of data is to use a box plot. Box plot looks something like this. You have, for each series of data, you have this box representing the region where the 50%, the middle 50% of our points are. So between quantiles 25 and 75. These are the boxes. So in these distributions, we have 50% of the data inside these boxes. Then we have these whiskers that tells us where is the maximum and the minimum of the distribution apart from outliers. So this is where our distribution ranges when we ignore the outliers. This red line here represents the median value. So you have the central point of our distribution, and then you can represent the outliers as individual points. And the outliers as defined as those that are away from the box more than 1.5 times the interquartile distance. So if you have points that are distance from the box more than 1.5 times the size of the box, they are considered outliers. These parameters can be changed, so you can fine-tune the parameters of the box plot, but this is the general idea. And so by looking at these box plots, you not only have an idea of where the median is and more or less the range of the data, but you also have an idea of the distribution by looking at those quartiles. So let's use this to look at the data on the diabetes indicator. We load our data, and now we can use this from our data, the box plot function. So we have the whole data set. We loaded the data into this table using those 3-letter codes for the different columns, and now we do the box plot with all our data. So you can save the figure if you want. This is not mandatory, but it's often useful to save the images if you're going to use them in a report. And I usually set the dots per inches value either at 200 or 300, depending on the resolution I want. And this bounding box tight removes as much space as possible from around the image. So it's nice to get the image in a document without having that large margin around. So if we do this, if we do the box plot with our data, the diabetes data, we see that we have a very strange thing here, because these are all in different scales. For example, the number of pregnancies is a small number, very close to 0, but the serum insulin concentration, depending on the units it's measured in this case it goes to 800. But this does not make sense to compare the number of times pregnant and the insulin concentration in the same scale, in the same vertical scale, because these units don't have anything to do one with the other. So the same thing for the glucose in the plasma and the age of the person and so on. All of these are in different scales. So this is one problem when you're comparing data or looking at either doing some computations with the data or visualizing data, that if you have different columns that have different meanings, their scales can be completely different and you cannot just compare them as they are. So we need to do some rescaling here in order to visualize our distributions better. So one thing we can do is normalization. Normalization is a rescaling operation that changes each of the series into values between 0 and 1. So basically what you do is you compute a new value of y for each of your points by from the original value that you have, you subtract the minimum of all your series, and then you divide by the distance between the maximum and the minimum. So by subtracting the minimum, you will force it to be at a minimum of 0. And then when you divide by the difference between the maximum and the minimum, the maximum value you'll have in this function here will be 1. So you go between 0 and 1 for all the values, and you rescale everything like this. So this is called normalization, and it's easy to do because we can compute these values on our data frame, and the mean function will give us an array with the minimum values for each column. We can subtract that from all our data set, our data frame, and this will broadcast the operation and subtract the minimum of each column from each of the columns over all the rows. So we can do this in one go for all the data points, and then we can also do this division here. So we can subtract the maximum from the minimum. This will be an array with the maximum values for all the columns. This will have the minimum values for all the columns. This difference will also be an array with all the differences for all the columns. So when we do this operation here, we are dividing each column by the distance between the maximum and the minimum. So it's very easy to do this normalization, or this is an illustration for any kind of these sorts of operations that you want to do. So if you need to do some operations that broadcast through all your rows or columns or all the table, you can do it easily like this. So now we do the box plot with the normalized data, and this is what we have. So in this case, you see all the data, the series, are in a range between 0 and 1. So you always have here 0 as the minimum and 1 as the maximum. But now we can see how they are distributed differently. For example, diabetes is only 0 or 1. So all of them fall inside the box here. The number of times pregnant has a few outliers here. The serum insulin concentration has lots of outliers. So it seems like to have a long tail distribution over there, and so on. So this can give us an idea of the shape of the distribution, and we have rescaled everything to make all the maximum values equal to 1 and the minimum values equal to 0. But this may not be a very good way of rescaling our data. There is one way, depending on how the data is distributed. You can also use standardization. Standardization, while normalization will get you everything between 0 and 1, standardization will get you everything with a mean of 0 and a standard deviation of 1. So all the series will be centered at 0 with a standard deviation of 1. To do this, you just subtract the mean of your values from each of the values, and then divide that difference by the standard deviation of all your values. This is also easy to do. So we take all the data series, all the data frame, subtract the mean of all the columns, and then divide by the standard deviation of all the columns. So this does this operation broadcast over all the columns, and then in each column over all the cells. So now we create the box plot again, and we have this result here. You can see the comparison. This is the normalized plot, so everything between 0 and 1. This is the standardized plot. Everything has a mean of 0. Of course, the median may not be the mean, but the mean is 0, and the standard deviation is 1. So depending on what kind of data you have, it may be better to do one or the other kind of rescaling, but in general, normalization is good when you know that your extreme values are fixed. For example, suppose that you're dealing with an image, and you know that each pixel, each color goes from 0 to 255 or something like that. And if you have a fixed range, then mapping that into 0 and 1 could make sense. It's not very good if data has outliers, because then the outlier will be at 1 or 0, and the rest of the data will be all compacted somewhere inside that range. Standardization is better when you have outliers, and especially when you have approximately normal distributions, because then you get most of your data around 0 with the standard deviation of 1. So it's around that interval of minus 0.5, 0.5, something like that. And then the outliers may be further away, but the outliers by themselves will not change your scale very much. But in any case, this may take some experimentation, but just remember that when you're visualizing these kinds of tables and the columns have different meanings, you should rescale your data in some way in order to match them more adequately. Another thing that we can do, what we do with box plots, is to look at the distribution of each feature, of each column, but we are not looking at relations between different features. So we cannot see how, for example, diabetes is correlated with insulin serum concentration or something like that, because we are just looking at the data in separate. But we can also visualize correlations, at least between two series at the same time. More than that becomes harder, but for two, a good way of doing that is with the Scatterplot matrix. So this is a matrix where you plot one feature against the other, and then you do a matrix of all these plots in a sort of table of plots, and it's good for visually finding correlations. In the diagonal, since the diagonal corresponds with combining one feature with the feature itself, you can put an histogram or a kernel density estimation and just have an idea of the distribution of values in the features. Pandas has this scatter matrix function in the plotting module, and you can do this scatter matrix like this. So we can use it with a kernel density estimation in the diagonal, or by default it's a histogram in the diagonal. So basically you call the scatter matrix with your data frame, and it will do all the combinations of columns you have there, and it will build something like this. So here you can see let's see it like, if we can do it like this. You can see for each pair of columns, you can see the scatter plot of combining one with the other. So if you look, for example, at these two, in insulin in the serum, and the second one is the is the glucose concentration, for example, you noted there seems to be some slight correlation here. This is also correlated, body mass index with this one is below. So with this, so this is the tricep fold fat and so on. So by looking at the data, you can find that some don't have any good correlations, but others seem to be, other combinations of features can be more correlated. So this scatter plot will do this automatically for all the pairs of features, and in this case the diagonal has the histogram, and then the if you want, you can use the diagonal with the kernel density estimation. So this is good for spotting correlations between pairs of features in your data. Of course, if you want higher order relations between combinations of more features, then it becomes very hard to visualize. But scatter plots are a good way of quickly looking at the data and see if you have highly correlated features. Okay, so this is it for today. I just have a few small things to add. So basically, to sum up, we saw in the previous lecture how to use Pandas to process our data, load the data, and organize it or select what we want, deal with missing values and so on. And now we saw some features for plotting with Pandas. If you look at the documentation of Pandas, you'll see that you have lots more options, lots more types of graphs and so on. So it's very good to, if you're going to use this, to actually look at the documentation, follow some examples, and use that as a reference. This is not something for you to memorize. It's something for you to know that it exists, so that you can look it up and use it as needed. We also use SciPy for kernel density estimation. Next week we're going to use SciPy for other things, for fitting models and so on. So that's another useful library if you're dealing with numerical data, especially if you're doing some modeling, simulations, and so forth. But for dealing with tables of heterogeneous data, Pandas is very good. One thing I didn't show, but you also have, is the ability to save your tables, your data frames, to Excel format, CSV, and so on. So even if you are not using data that comes as a table, when you generate your own data, you may find Pandas useful to organize the data and then save it and export it so you can use with other software. So Pandas is also good for data understanding, for that kind of exploratory work at the beginning, if you want something to quickly look at your data, compute some statistics and such, and also to generate reports, to do this kind of visual inspection of the data. Another thing that I didn't detail here, because you don't have this installed in Anaconda by default, but you can, if you go here to the data reader site, you can download this module. And this is a module for getting data from servers, directly from some services. So you have things from OECD, Eurostat, World Bank, trading, and so on. So if you're dealing with this kind of data for sociological studies, financial studies, things like that, this may be a useful thing, because you can directly query the servers and get your data as data frames, and don't have to worry about downloading things and converting formats and so on. This library does this for quite a lot of services like this. So I just put here a few examples, but if you use this kind of data, take a look at this library to see if it has the conversions, the objects for the servers that you need, and then it makes it a lot easier to just import the data into your program and use it as a data frame. Now, for this week, you have a very simple exercise for plotting with those contracts, public contracts data. You have the files there in the zip archive. But what I would recommend for you to do is to take this week for practicing and basically getting more familiarity with the basics of programming, because from now on we will be focusing on using these kinds of libraries. We will be revisiting this creating functions, doing loops and things like that. So we saw this here at the beginning for plotting the kernel density estimation. We did this for loop, we created a function. So we will be looking at these again and again, but now I will simply assume that I can show you this code and you will understand. So we can move on to more detailed tools like Pandas and SciPy and things for machine learning and so forth. So I recommend that if you're still not comfortable with the basics of Python, go through the exercises mostly from the first 2 weeks, also the third week with plotting and so on, but mostly those chapters 1 and 4, where I put a lot more exercises for basic programming. This part is not so much for exercising, because it now starts to depend a bit on what you want to do with Python in the short term. So I would also ask you to think about your final project if you want to do evaluation, or some useful application of Python, and start orienting your studying and your practice towards those specific problems. So if you want, you can write me an email and we can discuss that. So for the next 2 weeks, we're going to look at modeling with SciPy and statistics and fitting, adjusting models and things like that. And then in the last week, we will look a bit at scikit-learn for machine learning and for classification, regression programs and such. So those will be more in-depth looks, or a bit more, as much as 2 hours allow us to be in depth, but we'll be looking at the libraries and not so much the basics of Python. For these parts, NumPy, Pandas, and Plot, I recommend also that you take a look at the documentation online. Not so much to study for now, because you won't be tested on this, but just to be familiarized with what you have available, because this is a very good resource when you're actually working with these libraries and trying to solve some problem, instead of wasting too much time trying to experiment different things. Just look at the examples, the tutorials, the documentation for the different functions, and you have most of the answers there usually. So it's much easier to use these tools if you are familiar with the documentation. Okay, so let's take a short break, and I'll start the Zoom meeting at 7. If you have questions, then I can answer them at 7. Okay, see you soon.